Hello! In this video we're going to cover sections 1.2 and 1.3. We'll see why we merged them together. 1.2 is an application of inductive reasoning, number patterns. So inductive reasoning again is when you look at specific elements and try to make generalizations based on those specific elements. And finding patterns in things is a very good example of using inductive reasoning. Before we get to examples though, and I forgot to load up the thing. That's going to load up over there, which I'm going to move over here, and you're just going to hear me say things, and you're just sitting there like, oh my gosh, when does he stop talking? The answer is usually never. And then, yeah, there's that one. Okay, good. I'm ready now. Okay, so the first major topic in this section is the idea of a sequence. You may have already heard this word before, and you might have a general idea from it. But a sequence, for our purposes, is just one number after the other. I think that's a very basic definition. There's a very hardcore mathematical definition that would occur in a higher level math class, so we don't have to really worry about that. But one thing to understand is that don't assume that all sequences of numbers follow a pattern. In this class, they're going to be rigged to follow such a pattern, and there's going to be three major types of sequences. They are going to be arithmetic, Arithmetic is when you keep adding the same number repeatedly. So, for example, I don't know, 3, 10, 17, 24, 31, bop, bop, bop. I keep adding 7. So this would be an arithmetic sequence is the formal name. And the number I keep adding is 7. And just in case the book asks for it as a homework, 7 would be called the common difference. And the reason it has that name is because if you subtract the second from the first and the second and the first and the third and the second and the fourth and the third, the common difference is 7. So if you keep adding the same number over and over again, arithmetic. If you keep multiplying the same non-zero number over and over again, it's called geometric. I literally cannot believe how good my handwriting is. If you think that's terrible, just wait. Seriously, it gets so bad. Geometric is you keep multiplying the same number repeatedly. The same, I should put in there, same non-zero number. By the way, for both arithmetic and geometric, this number could be positive or negative. So, for instance, if we had 1/2 and -1 and +2 and -4 and +8, up, up, up. What number do I keep multiplying by to get the next number? Hopefully you thought -2. And the term associated with this magical number for a geometric sequence is called the common ratio. So yeah, it could be positive or negative. It does not matter. When the signs of the numbers keep alternating, like here, this is +1/2, -1, +2, -4, +8. This is formally called an alternating sequence. So in total, we could call it an alternating geometric sequence. So the next time we're allowed out, you can bust that out at a party, and your guests will leave. Okay. The third type of sequence that we're going to have is called a, oh my gosh, I forgot the word. That's it. Successive difference. To be honest, this is best demonstrated via an example, and your very first video for this section is video number 3, Arithmetic, Geometric, and Successive Differences Sequences. But the whole idea is that in a successive difference, the original list of numbers doesn't seem to have any pattern. But what you do is you keep subtracting until you get down to an arithmetic sequence, and then you build back up. So sort of like there's a code in between a secret arithmetic built into your given sequence. So when you're asked to find the next term of a sequence, go in this order, basically. Ask yourself, okay, can I add the same number to get the next number? If so, use arithmetic. If that doesn't work, ask yourself, can I multiply by the same number to get the next number? If so, great, it's geometric. If that doesn't work, then try this successive difference thing. If that doesn't work, well, maybe there's not a formula per se that you can use. But also the alternative is maybe there's no pattern. That's completely possible. One very, very good example of that is the number pi, 3.14159, and then it just goes on forever. There is no known pattern to make the number pi. You can watch the movie Pi on a very small screen, which is related to that idea of trying to use the digits of pi to predict things. Again, very small screen. It's all shaky cam. Soundtrack is phenomenal. You're welcome. But if you would, pause this video, go check out video number 3. Welcome back. Okay, so now that we have an idea of how to find terms of a sequence, now what we're going to do is start adding up those terms. And we have 2 major subcategories, the sum of odd numbers and the sum of even and odd numbers. And you might ask, well, why don't we have the sum of even numbers? We'll get to that later. So what we're talking about here is, let's suppose we wanted 1 plus 3 plus 5 plus 7 plus 9. Well, this is a very small list, and you probably can just add them up, maybe even in your head, and not have to worry about anything fancy there. But there is a shortcut, especially if you have a longer list of numbers. And if that longer list of numbers is of the form, nope, that's not what I wanted to hit. How's green? Are we okay with green? 1 plus 3 plus 5 plus... And this sum just goes on for a while, but then we end up at another odd number, but has the format 2n minus 1. I'll explain. If you were to add, starting at 1, that's very important, all the way up to some odd number, which has the format 2n minus 1, that total sum is equal to n squared. Couple things. 1, what is this n? Well, n is the number of numbers. So keep that in mind. Actually, I'll write that off to the side. N is the number of numbers. Always. That doesn't look like an n. Now it sort of does. Now it's an n with the top hat. Fancy. Anyways, going back to the example in blue, 1 plus 3 plus 5 plus 7 plus 9. How many numbers do we have there that we're adding together? Hopefully you said 5. There's 5 numbers. 1, 3, 5, 7, 9. Awesome. Well, let's talk about where this 2n minus 1 comes in. What is 2 times 5 minus 1? 2 times 5 is 10, minus 1 is 9. So notice we have this pairing up here. Here's our 1, here's our 3, here's our 5. The dot, dot, dot covers anything in between. And at the very, very end, we have our number of the format 2n minus 1, where n happens to be 5. We knew it was 5 because we can count how many numbers there are, odd numbers from 1 to 9. Well, this sum, 1 plus 3 plus 5 plus 7 plus 9, will equal n squared. Well, for this blue problem, our n is 5. So this sum, 1 plus 3 plus 5 plus 7 plus 9, is equal to 5 squared, which is a friendly 25. So the first task is to figure out what this n is, which might not be obvious. So we'll do a really short example because there are videos for this. So pick an odd number, any odd number you want. Make it exciting. And yes, I can totally hear your thoughts. Good job. You said 211. Fantastic choice. I am not going to sit there and write all odd numbers from 1 to 211. I've got video games to play. We all do. So what you do off to the side is you take that odd number, 211, and you set it equal to 2n minus 1. We're going to do some algebra, but it's not too bad, I hope. We'll add 1 to both sides. We get 212 equals 2n. And then how do we solve for n? We divide by 2. Yes, we divide by 2. That's exactly what you said. I think that's 106, he says. So what that means, and this is not our answer, by the way, there are 106 odd numbers from 1 to 211. So to figure out the sum of the odd numbers from 1 to 211, according to our formula in green, this would equal 200. I'm sorry, brother. Ignore that. I'm not editing that out. This would equal 106 squared. And now he doesn't know where he put his calc. It's in the other room. Oh, calculator. I'll use you. I choose you. So if I do 106, don't ever use this calculator. It's so terrible. Squared. 11,236. So the sum from all the odd numbers from 1 to 211 is, I forgot what I totally said, 11,000. I know you're saying it out loud. Again, I can't hear you. 236. And that's your final answer. So the two-step process is figure out how many numbers you have. We had 106 odd numbers. And then the sum of those odd numbers starting at 1 to that odd number at the end there is that number squared, 11,236. On the flip side, what if we had evens and odds? Boop. So 1 plus 2 plus 3 plus 4 plus boop, 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 plus 9. I'll use 9 again, it's fine. When you're going from 1 to 9, how many numbers is that? There's 9. And that's why starting at 1 is very, very nice. You'll see some examples where you don't start with 1 in the videos. You'll be okay, I promise. Because we have 9 numbers, then we can go right to the formula. Let me write down the formula in green again. 1 plus 2 plus 3 plus dot 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 plus n. So this time n is the last number instead of 2n minus 1. The formula is not as nice, unfortunately. It's okay when you put it in the calculator. N times n plus 1 over 2. So in our blue example there, we are adding 9 numbers. So n is 9. So we'd have 9 times 9 plus 1 over 2. All right, that looks horrible. But if you put in your calculator top to bottom, so 9 times parentheses, 9 plus 1 parentheses over 2, you'll be fine. We could do this in our head. 9 plus 1 is 10. 10 over 2 is 5. 5 times 9 is 45. By the way, that's my dog, Marsh. He is going to town on a toy, which is fine because that means he's not eating shoes. My secret stash of donuts. The important things in life. So, if you have odd numbers starting at 1, you find out how many numbers you have, setting the last number equal to 2n minus 1. Solve for n. Whatever that number is, that's the number of odd numbers you have in this case. And so you just squared, and there's your answer. That's the sum of odd numbers. If you have even and odd numbers starting at 1, the last number is the number of numbers. then you just throw that into the formula, n times n plus 1 over 2. Whatever answer you get, you're good to go. The reason you don't need a sum of even numbers is this. Let's suppose we had 2 plus 4 plus 6 plus 8 plus 10 plus, let's go up to 18. I like it. The reason you don't need a special formula just for even is, what does it mean to be even? Hopefully you are thinking of something about the number 2, right? To be even, that means it's divisible by 2. In other words, 2 is a factor of that number. Well, I just said the F word. If we factored out that 2, if I take out the 2 from 2, I got 1. 2 from the 4, I got 2. 2 from the 6, I got 3. And then 4 and 5, and then up to 9. The reason we don't need a special case for just evens is because even is just a special case of sum of even and odds. Notice here, we previously found, right here, the sum from 1 to 9 to be 45. So we have this 2 times that sum, 45. 2 times 45 in most countries is 90. All right. So in the video, as he looks, which is video number 4, you have like 6 examples of this. I guess it's a longer video. So we'll do some ones that are sums of odds, sums of evens and odds, and then some special cases. One of them, I think, is a multiple. Yep, there's an even one there. And then another one is, what if you don't start at 1? Bum, bum, bum. Well, you manipulate those formulas, is basically what it boils down to. Now, as a comment, those formulas in green will appear on your midterm. You just have to know how to use them. If you have questions on that, please let me know. So if you would, watch video number 4, and then come back for section 1.3. Freeze frame. Freeze frame complete. So section 1.3 is strategies for problem solving. We all have problems. And I have no strategies for you. I'm so sorry. But this section, unfortunately, there's really not much to teach. And the reason being is because this section is the only section in the entire class that is pure potpourri. He says that lying because there's another section in chapter 5, but don't worry about that. So the purpose of 1.3 is to take word problems. I said it, I'm sorry. And just trying to use logic to figure it out. Sometimes you might have to draw some pictures. Sometimes you might have to come up with some examples. I would try to imagine you are doing these word problems. Like one of them is going to deal with shaking hands. So just picture like people shaking hands, things like that. There is some strategies in the book, and I'll ask you to definitely read those. But one humongous thing is, just because example 1 deals with coins, don't think that all problems that deal with coins are going to be solved the exact same way. It's not going to be the case. If you've ever played any apps in your phone, like The Room is a fantastic one, then you'll probably be better geared for this section, because games like that are pure inductive reasoning gold mines. Just thinking about, okay, where did I hear that sound before? Where did I see that symbol? Let me apply it here. Like, for instance, in these types of games, you find a key, maybe on the ground, and so your first thought is, okay, there must be a keyhole for this key. Let me go find it. Great. You're halfway there for this section. So if you have anything specific, you will get some headaches. I apologize, especially in the homework. Let me know as always. All right, so that is that's this video for 1-2 and 1-3. Hope you're having a great day. Bye. Oh, I have to hit stop.